Hello, everyone. I am Ed Pegg Jr., your host for this newest edition of Mathematical Games. This is a series of talks that basically celebrate the works of Martin Gardner, who ran the column Mathematical Games for Scientific American for 25 years. These were collected into 15 books, and they were highly inspirational to many mathematicians who grew up in the 60s, 70s, 80s, and 90s, and anybody who's looked at his books. He basically collected the whole field of recreational mathematics in basically a way of making mathematics interesting. And that helped me a lot when I was growing up. So we have many different demonstrations and demonstrations.wolfram.com that deal with distances, and I'll be touching on a few of those demonstrations in my talk today. So, oh, and I've got a typo right there right at the start. Martin Gardner asked about what matchstick graphs could be built without overlap in one of his early columns. And a matchstick graph basically uses items of fixed length, and you put them together so that they meet at their ends. And that's a unit distance graph, basically. So a triangle, like shown here, is a simple one, an equilateral triangle. And he shows all the different ways of putting five matches together to get unit distance graphs, and he comes up with 10 different graphs. But he actually misses two, and none of these show a triangle that has one vertex extended by two. He's got uh, two different ways of using an equilateral triangle, but he misses this one. He also doesn't have a line of five matches with an extra match at the center. So there's actually 12 matchstick graphs with five edges. And he goes on with a puzzle to ask for the number of matchstick graphs with six matches. And there's actually 28 of them, as shown here, and 74 if we go to order 7. And all of these are in graph data. One question I wondered when having this talk is, what is the smallest figure that requires overlapping to make the figure? And I believe the 3 prism is the smallest, but in graph data it looks like this. So I came up with a function to find the unit distance embedding when we had it, and here's what that matchstick graph looks like. It's a way of joining 9 matches, but to make this figure, you'll need to have at least one overlap somewhere. You can't get to this planar case with all the edges having the same length. So one thing we can do is just collect the vertices, and I showed 2 ways of doing it. I've got a piece of code which will grab the unit distance embedding from graph data if it exists. But there's another way you can do it. You can just do this. You can ask for all the embeddings which are unit distance. That's an easier way of extracting those out of graph data. So here's a set of vertices for this graph, and we can make a picture just from the vertices. This is a piece of code which will just use the vertices, and based on those, we'll find all of the unit edges and then make that graph. So these are 2 pieces of code that I'll be using in my talk. And let's see. So far, and I see a question here from Dugan. So far, all the graphs here are restricted to 2D space, but I'll be talking about graphs going to 3 dimensions and 4 dimensions eventually. So here are other regular matchstick graphs where 3 matches meet at each vertex. Here's the minimal way of doing it so that there's Excuse me. Let me get a drink of water here. Here's the minimal way of making a matchstick graph where 3 meet at each edge and there's no overlaps. Most of the rest of these do have overlaps. Not the Peterson graph, though. There's one way of doing it with matches so that you get the Peterson graph. These are various graphs that can come out of it. Here's a object known as the Dürer graph, which is based on this curious piece of art by Albrecht Dürer, which is a famous object in recreational math just because he put in so much, such as a magic square and many odd objects of interest in mathematics and science. If we go to vertex 4, the minimal known example is what's called the Harborth graph, which Martin Gardner would have put into a column, except that it was discovered right as he was closing out the last column. So this never showed up in mathematical games, but it would have if it had just been discovered a year earlier. There's many other quartic unit distance graphs, and here's a few of them. For example, the tesseract is one. Here's a way of bracing the pentagon, which we'll discuss very soon. This here is not a way of bracing the nonagon. This is not a rigid graph here. So some of these are curious graphs with various different properties. One thing you'll see in quite a few of these are torus graphs. So, for example, this torus graph is a way of arranging 8 squares in a torus. So these are all from graph data, and we'll be covering a few of these graphs in a little bit. How about valence 5? Well, one thing we can do as Martin Gardner discussed in his column on hypercubes, is you can just take the object, shift it in any direction you want by one space, and with those 2 copies, they're all separated by length 1 edges. That's basically how to do a graph product of a graph with a path graph. So basically, each of these is taking the previous object and shifting it in a new direction 1, and you get a slightly larger graph. Here's an easier way of seeing a graph product. We have a triangle and a diamond. And when you combine those together, you get 4 triangles and 3 diamonds. So that's a way of getting a graph product of a triangle and a diamond. And most of the unit distance torus graphs are based on that concept of a graph product. Another way of getting a valence of 6 or 8 is to use the Hamming graphs. That's what these are. This is the Hamming 3-3 graph used in error correcting codes. Curiously, even though this graph looks like it's got a whole bunch of bracing triangles, it's not a rigid graph, and you can deform it. These are the same graph here. Well, the one is just basically deformed, even though everything is unit distance edges. You can still mess around with the graph by moving vertices around. This is a larger version of the Hamming graph. This is the 4-3 version, and it has a valence of 8. Every vertex connects to 8 others. Here are 2 more sextic graphs. This is one I found about 25 years ago. I was just basically running a search for how to do star polygons that would link to different levels of each other. And I noticed this one. And this got put into graph data back at the start, and it wasn't all that interesting a graph for about 20 years, but then it became important later. And this is the Jeter graph, which is related to weakly regular graphs. The capital of one of the European countries starts with LJ. I forget how to pronounce it. And it's based on the graph named after that capital. Another column Martin Gardner looked at was bracing the square with unit distance lengths. And he asked if it was basically possible to brace the square just with matchsticks, basically. And these were two solutions that he knew, but readers came up with this method here, which also works. And this method, if you realize that points A, B, and C have to be collinear, you can see that this is rigid. This is not a rigid graph here. It can be deformed, and this is not a proper bracing because this length here is greater than 1. So this is from one of his columns, and we've got graph versions of some of these. This is a overlapping version of one of the first brace square examples, and this is a overlapping version of the 23 rod solution. This is a more curious way of bracing the square that looks a lot stranger, and also it doesn't use any triangles. It's a triangle free, which you can see from looking at the girth of the object. The girth is the smallest cycle in a graph. The first two and this last one obviously have triangles, but this one has no triangles. So this is a way of bracing the square without using any triangles. We can also brace the pentagon in various ways. This is a way of doing it without any overlap. And this version and the second and third version don't use any triangles in their bracing. Bracing the hexagon is easier. If you use triangles, you just add a few. But if you don't use any triangles, it's much harder. And here's a way of bracing the hexagon without any triangles. So bracing the heptagon, I showed this graph a few minutes ago. Well, it turns out if you divide this up into 3 parts, basically, you get this graph, which has a heptagon in the middle. And this is another graph that I found years ago. And eventually I asked, well, is this a rigid graph? And it turns out the answer is yes. In fact, it's so rigid that you can take any 2 connected vertices anywhere and rip away everything supporting them, and whatever is left is still a rigid object. So here in this version, I believe this edge and the 2 supporting vertices and everything else connecting to those vertices was removed, and it's still a rigid graph. So this basically sets a record for bracing the heptagon, and it's something I discovered accidentally. Here are 2 other ways of bracing the heptagon using more struts. We can brace an octagon, and here's ways of bracing the 9, 10, 11, and 12 gons. We can go up to, well, we can go up to any size, but here's a particular way of bracing the 18 gon. But I've often wondered about this shape here. This is called the Hirshhorn medallion, and it's a way of dividing the 18 gon into 18 identical pentagons. Irregular pentagons, but they're still the same shape. So I've wondered for a while, what is the fewest number of struts you could add to this shape to make this rigid? Another way of getting all the edges the same is to look at a lattice graph. For example, if you just used a simple square lattice, the edges here will all be the same length. And if you use a night move or a camel move, or a zebra move, which is a 2-3 move. The camel is a 1-3, the knight is a 1-2. Those are all different ways of making sure that all the edges are the same. That also works on a triangular grid. We can just use the nearest one, or we can skip one, or we can do two other strange moves here. You can also look at the hexagonal grid for another case of where you can pull points off and get all lengths the same. So as a slight segue, you can express 1729 as the sum of two cubes, and that's well known. This is known as the taxicab number due to a story between Hardy and Ramanujan. But fewer know that 1729 can be expressed as the sum of three squares in six ways. I certainly didn't know it, but Power's representation is very handy for coming up with these facts. But it's more useful to find ways of moving around in 3D space that have the same length. So for example, if you want to move a distance of 3, or 3 squared here, basically you can use Power's representation and find that, well, 0, 0, 3 in any direction will move 3. But also if you move 1, 2, and 2 in 3D space in X, Y, and Z directions, or any variation thereof, you'll be moving 3. And Serhii Grabarchuk noticed that if you take a 4x4x4 grid and look at all distances that are exactly 3, either 0, 3, 3, 3, 0, 0, 3, for example, vertex 4 here to 52, just basically a straight line, that's a distance of 3. But also if you do down 1, over 2, and back 2, 52 connects to vertex 27 here. And it turns out that in this cube, every vertex connects to exactly 6 others. And that's a curious amount of regularity for a leaper. So this is known as the Grabarchuk graph. Serhii Grabarchuk and his family do a whole bunch of nice puzzle books, and this was something he found while building one of his puzzle books. So there's another lattice we can take a look at. So let's take a cubic lattice, and we want to make the densest possible packing of non-overlapping spheres. How could we do that? Well, this is not the densest packing here. The trick is to use the face-centered cubic packing, which is one of the two densest packing uh, uh, two densest sphere packings. And the way of coming up with that lattice is to choose points that are either all odd or all even. So here's code that will do that. And we can get a sample of the FCC lattice this way. So here, all the values, X, Y, Z values are even. Here, they're all odd, all even again, all even, all odd. So that's one way of building up the face-centered cubic packing lattice, is to just pick points that are either all odd or all even. And here we can grow the sphere packing until it fills the cube. So this is the densest packing by spheres from those lattice points that I started with at the top. By picking out all the even vertices, and the all even vertices and the all odd vertices will fit together very nicely for packing spheres. So I mentioned the Grabarchuk graph. are there any other regular graphs that come out of grid graphs? Well, one of the curiosities is the 5-leaper on the chessboard. So the Pythagorean triangle is a 3, 4, 5 triangle with a legs of 3 and 4 and a hypotenuse of 5, because 3 squared plus 4 squared equals 5 squared. If you combine a 3-4 move and a 0-5 move, you get the 5-leaper. So for example, this vertex this vertex connects to that one, this one, and these two, off by 3, 4, and 4, 3. And it turns out that every vertex in the 8x8 grid is exactly a distance of 5 from 4 others. So this is a quartic graph. And you can check that with, it is a regular graph in graph data. I wondered if there was another lattice graph that was regular from the FCC lattice. And I found this one here. This is a regular graph. Every vertex connects to exactly 6 others. And all of them are 1, 2, 3 leapers, or square root of 14. So this is another curious regular grid graph, but this time the lattice is the FCC lattice. The chromatic number of a graph, for the vertex chromatic number, you basically want a vertex coloring where for every edge, the different ends are different colors. So for the square grid graph, you basically just need to use a checkerboard pattern. And for the hexagonal graph, you basically have the same color at the bottom of each hexagon and the other color at the top of each hexagon. These are 2 colorings of basic lattices. If you go to the triangular grid, you need 3 colors for a vertex coloring. The Peterson graph and the Hamming graph also need 3 colors. But there are cases where 4 colors are needed. For example, the Huffman-Singleton graph needs 4 colors. The complete graph on 5 points needs 5 colors, complete graph on 6, and so on. It's not known with the Huffman-Singleton graph is a unit distance graph, though. But here's a case that does require 4 colors. This is called the Moser spindle. Suppose you tried to only color this in 3 colors. So we could start with this diamond over here. We need 1 color here. We need 2 other colors here because we have a triangle. And the only way to stay with 3 colors is to color this vertex the same as that vertex. But you also have another diamond over here. If you use the same argument, you'd need to use this color down here as well. But that would put the same 2 colors together. And so this spindle requires at least 4 colors for a vertex coloring. The Golem graph has a similar argument. You basically start with the triangular grid. You basically need to follow for the hexagon, you need to follow the coloring of the triangular grid, which would put the same color at each of these vertices. So this triangle in the center would need to be colored with just 2 colors in order not to conflict with the triangle of 3 colors that have to be the same, but that's not possible. So the Golem graph requires at least 4 colors to be vertex colored. Here's a stranger graph here that requires 4 colors. And the Yule spindle is a newer one, which requires 4 colors. This one came up to be important just within the last few years. There's also many more of these graphs that would require 4 colors, and we'll get to those fairly soon. So a famous problem in both recreational mathematics and recreational geometry, geometry in general, and combinatorics is the chromatic number of the plane problem. What is the fewest number of colors so that no 2 points of the same color are exactly 1 apart? Well, one way of doing this there should be 7 colors here. One way of coloring the plane in 7 colors is this method here. So these hexagons, red hexagons, their distance from one corner to the other is 1, and the distance to another hexagon is slightly more than 1. So this is, and it basically repeats for all 7 colors. So this is one way of coloring the plane with just 7 colors so that no 2 points are a distance of 1 apart. But we can almost completely eliminate one of the colors with this method. So here we have very, very tiny white squares that represent about 1 over 300 and 1/300th of the plane. It requires this rather strange polynomial here. Let's see if we can make that a bit larger. This is a order 16 polynomial that's necessary for making this figure. And you basically need a value of x about 0.04. And one of these triangles has vertices of 0, 0, 0.04, 0.04, 2 times 0.04 or 0.08 and 0, and 0.04 minus 0.04. So that's one of these tiny white squares here. This is another way of coloring the plane with 7 colors, but 1 color isn't used all that much. Here are some of the unit distances seen in this graph. For example, the distance from this point here to this edge is 1. The distance from this vertex to that one is 1. From this vertex to that one is 1, and so on. These black bars are different unit distances for this coloring. And this is something that I found about 25 years ago. Alex Soifer used it in the original version of the mathematical coloring book, which discusses this problem of the chromatic number of the plane. So we know that coloring the plane needs at least 7 color, or needs 7 colors or fewer. And with these spindles, I showed this one in the Golem graph. We can use this to show that it needs at least 4 colors. And here's the Moser spindle again. This shows that we need at least 4 colors to color the plane because of this object. Because if you have a coloring, you can basically toss this object onto the plane. It will mark 4 points that require 4 colors. A larger question is, what is the minimal number of colors you need to color space? In space, there's probably a spindle that might work similar to this, and there is. And here's what that spindle looks like. You basically have a series of tetrahedra, and basically this point would have to be the same as this point over here for 4 coloring. You're basically, the object is you want to show that this has to be at least 5 colors. Well, you start by proving that it needs that 4 colors isn't enough. So if you if you use a series of pyramids, for example, these 3 points here both connect to these two, so these two would have to be the same color. And when you repeat that with this object, you basically get that these two colors uh, would be forced to have a certain property, but then that messes up with this point or another. So this object can be proven to need at least 5 colors to be made. A similar object is this shape here with a more complicated argument. And another is what I call the double Pac-Man. It's not clear to see, maybe perhaps like so, but basically this is if you take four tetrahedra and glue them together in a sort of a circle, you can get maybe this one here. This, well, I'm vaguely showing something, but this tetrahedron, uh, this point, that point, this point, this point, and that point make a somewhat Pac-Man shape. And then there's another Pac-Man this way. And when you combine them together, you can basically show that the way those vertexes line up would force two vertices to conflict, and therefore this needs at least 5 colors. It turns out that you can do better. This is a much more complicated graph, which proves at least 6 colors are needed to color the plane. This says chromatic number 6, and I've completely forgotten what the argument is for this figure. It was found by Audrey de Grey and Hogstrup. So another question we can ask is, what is the maximal number of edges needed if you have a given number of vertices? For example, with 7 vertices, we can prove that the maximal number of edges you can get is 12 if you arrange them in a hexagon. This is known as the Erdos unit distance problem. And there's a paper which I'd link to. And by the way, this whole talk will be online sometime soon at Community. Here are the best known examples, or here are the best examples up to 15 vertices, or maybe 16. And here's some examples for slightly larger cases. It's unique for this number of vertices, and various solutions at the end here. Some of these we had in graph data. We had this one in graph data earlier. And these will be added to the next version of graph data sometime soon. Here's the last of those graphs. And we have a combination of 2 graphs here. There's this one is unit distance 16.2, shown here, and unit distance 16.1. And basically, if you look at this pentagon, that's the Moser spindle flipped on the edge, and then we add 4 more points. This Moser bundle is a nice way of getting a dense packing. And if you take these 2 graphs and combine them, you get this shape, which was one of the end graphs in the previous version. So there's a overlap of nice unit distance graphs that comes out. It turns out there's a little bit of if it's a good idea in one graph, it's often a good idea in another graph, and when you try to extend them, you wind up using the same points over and over. If we keep extending this graph, if we find the best points to add to it, we get this graph here. which has 79 edges. However, the Hamming 3-3 graph has 81 edges. So this is not maximal. So the route that this was taking uh, uh, hits a dead end, but we don't know where the dead end is. This is it's unsolved what the next case is for maximal unit distance graphs. We know that the Hamming graph might be the best version for 27 vertices, but we're not entirely sure on that either. So this is an unsolved question. Here's a few other small unit distance graphs. Generalized quadrangle. I'm not sure of an easy way of describing generalized polygons, but they're very handy in both graphs and in other fields. We just showed the Golem graph and the Brace square. This dense graph here is triangle free and has various weird properties. And also the fish graph is a way of bracing the square without using any triangles. We can pull out some larger graphs. So here's a group of unit distance graphs, including the braced heptagon. And I kind of like those, how those look. So here's a whole bunch of unit distance graphs. The crossing number graphs are in, well, let me show one of them here. Let me grab this. The crossing number graphs, the question is, what is the fewest number of crossings in a graph that is possible? So, no, that's not the right embedding. Maybe if I do 7b instead. Yes. So here's a graph with 7 crossings, and this is the fewest number of crossings for this particular graph. There's a total of, I believe, 5 of these cubic graphs on this number of vertices that require 7 vertices or 7 crossings. And this is something I identified with GeoffXU a few years back. These different crossing number graphs are special cases where an exact number of crossings is possible and you can't get fewer. But they're also it's also possible to do them as unit distance graphs, but then their crossing number goes up. A snark is a graph which requires 4 colors. The Nauru graph is a curious cubic symmetric graph that's also a map of how you can roll an octahedron and get all its various permutations for which face is up out of the 24 permutations. So these are many different types of graphs. For example, the Goldberg graph is a variation of the snark. And so on. So these are the Tut 8 cage is the a cubic symmetric graph, which is the smallest cubic graph, which has a girth of 8. And this is one way of drawing it with complete symmetry, where all edges are unit distance. And we can extend this to larger unit distance graphs. The hypercube, the Bluenose scark was one of the earlier cases of a 4-colored graph, similar to the Peterson graph. uh, I forget who asked the question, but the Peterson graph was known to use uh, four colors, and they wondered for the edge coloring, and they wondered if there were other cases that of the sort, and the snarks is what Martin Gardner called them when the first ones were found. Here's the Hirshhorn medallion again, and the Foster graphs, such as this one here. These are different ways of building cubic symmetric graphs where all the vertices are equivalent to each other. It turns out that this particular case, Foster 042A, is related to the moving day problem. If you have a 2 by 3 grid and you put 5 objects down on this 2 by 3 grid, you basically want to swap the position of two items, a moving puzzle. It turns out that the positions of that particular puzzle on just a 2 by 3 grid with 5 objects on the squares is equivalent to this graph. So these are all interesting graphs of one sort or another, and these are unit distance embeddings for them. I mentioned the Foster graphs. The first few of these are famous for being cages. This is the smallest graph with a cubic graph with a girth of 6. So the smallest cycle in here is 6. And a Mobius-Cantor graph is similar. Also the Pappus graph. The Desargues graph, I forget what, there's something I've forgotten here, but these first few graphs are, I believe they're cages. I'll need to catch up on my facts a little bit later. So these are our unit distance embeddings for these famous graphs. So I mentioned the Moser spindle and the Golem graph, and I started looking for a solution for the chromatic number of the plane about 9 years ago. And I had this feeling that if I had the densest possible graph, I could find a set of points that forced a 5 coloring. So I came up with this. I started a search, and this particular set of points had a whole bunch of different Moser spindles and Golem graphs in it. So I played around with that, and one thing that became clear to me was that all of the points were in the algebraic field of square root of 33. I could represent everything with that algebraic field. So I started doing a heavy search within that field to come up with more and more points. However, it's not the case that unit distance graphs are always in this particular field. For example, this fish graph, also called the Hod fish after Hodgsburg O'Donnell, this uses a different polynomial of degree 12. But a whole bunch of different unit distance graphs, which required 4 colors, were in this field. So I wanted to study that. And Aubrey de Grey took interest in my graph, and we started a correspondence looking at the problem. And after a number of messages, I basically was suggesting that we could stay with square root of 3 and square root of 11. But Audrey was thinking, no, you need more than that. I think you also need square root of 5 and square root of 7. Need some of the graphs from that as well. Although it was fortunate that, excuse me, it was fortunate that he ignored me, because he wound up solving the problem for the chromatic number of the plane. He found this graph, which requires 5 colors, and that was one of the major discoveries of, I think, 2018. So it turns out that I almost prevented one of the greatest discoveries in mathematics. So it's a good thing that he ignored me on that particular piece of advice. So this is now called the de Grey graph, and they steadily found smaller and smaller versions of it. The smallest currently known is this one here, which requires 509 vertices. Dr. Parts and Dr. Yule have been kind of trading back and forth for coming up with the smallest graph, and this seems to be the record holder. Now, one thing I believed about unit distance graph that had chromatic number 4 was that they were rigid. Well, it turns out that that's not the case. Here are 2 of the graphs I showed earlier. They are not rigid graphs. These basically show how the deformation works. Oh, I mentioned that the hodfish breaks the square. Well, obviously it doesn't. It's not rigid. So here are other graphs that require 4 colors. The Yule spindle, I just mentioned Yule on the last page. Let's go back to that. For example, this graph here and this graph are both found by Yule. He found that this spindle here is also just as useful as the Moser spindle, and he used that fact to prove that his graph needs at least 5 colors. I found a few of these graphs that are shown here, but it really didn't, the graphs I found didn't have much of an impact on the problem. I showed the maximal unit distance graphs in 2D. Well, you can also look at the same problem in 3D. So here's the octahedron is one example of a maximal graph. Adding a tetrahedron will be a record setter. You can also fold it on the inside like so. You can combine 4 tetrahedra. Here's the Pac-Man shape I was trying to show earlier. If you take 2 of these and combine them together, you can get a object that forces 5 colors in space. Let's see, yeah, this vertex here, if this was 4-colored, in fact, you can 4-color this one, but this vertex has to be the same as this vertex, which has to be the same as this vertex in a 4-coloring. And when you combine 2 of these Pac-Man objects, you can get a conflict between these 2 colors. There's various ways of combining 4 pyramids, but then it starts getting stranger. This object here, using a pentagram, is one of the record setters. And some various other objects here. I forget when they start getting strange again. Here's a combination of 5 pyramids. You can see that these almost overlap, but not quite. This is one reason why the tetrahedra cannot fill space, and they can also overlap like so. Go towards the end. Everything eventually starts going to a lattice based on tetrahedra and octahedra bound together. For example, this object here. You basically get this overlap because you've got the tetrahedra penetrating all of the octahedra and also a vice versa effect. However, we're not sure if this continues going or if you get other strange graphs, because you can also do graph products and get objects with a high vertex count as well. And also strange things start happening when you get to enough points. So we're not quite sure about this one either. For the fourth dimension, there's another paper by Jiafexu, which has high chromatic graphs in the fourth dimension. But I'm not completely sure I've got this paper figured out right. So don't trust what I've got on this page too much. I'll keep looking at this paper on the chromatic number of and it basically, if you look for our 4D maximal and chromatic number, you can find this paper, and there'll be a link on community once this has been posted. For another distance-related item, I thought I'd bring up my plastic pyramid. So you have a set of 19 points here, and we have a little program here to determine if it's an exact power distance, if 2 points are an exact power of this value here. And it turns out with these 19 points, every single pair of points is an exact power of this, which is the square root of the plastic constant, which is x to the third minus x minus 1 equals 0. The real root of that is the plastic constant, about 1.6 something, I think. I've forgotten what the plastic constant is already. Let's find out. Uh, 1.32, right? And every object in every set of points here is exactly a power of for the distance. So it's very curious that these 19 points are all an exact power distance apart from each other. I don't know of any other object like this. If you try this with other constants like the golden ratio and the super golden ratio and other constants or integers or rational numbers, usually the best you can get for everything a power distance, the best you can get is usually 5. With the golden ratio, you can get up to 12. So it's really weird that you can get up to 19 with the plastic constant. There's a few unsolved questions. Is the odd 4 graph or the Hoppen-Singleton graph, is it a unit distance graph? And there's also a whole bunch of other graphs that we're not sure if they're unit distance graphs or not. What is the maximal unit distance graphs above 20 vertices? There's many that we don't know. And what are the bounds of the Erdos unit distance problem? Also, the rational distance problem, can a point be a rational distance from all 4 vertices of a square? That's unsolved. I have a demonstration that goes into that. It's very easy to get 3 points that are a rational distance from a vertex, and I list a few thousand examples of that. I basically used the data by Sasha Kurtz that was compiled by Randall Rathbun. They posted thousands and thousands of Heronian triangles. And I used that data to come up with the data I used for my talk on the rational distance problem. And he found that data and he liked it, but he noticed that I didn't use all of his Heronian triangles. And so he did it for everything. He also extended his list to a much larger set. And apparently he's found something, but I'm not sure what it is yet. So this talk will be posted on Community sometime today or tomorrow. And that's all I had. I can answer any questions that anybody might have, if anybody has anything. All right, many thanks for attending my talk then. And I'll see you next month with another episode. Many thanks.